Hello, guys. Hello, everybody. Welcome to my white world, to my whitey channel. I am a singer, eternal voice. Okay. So previously, I'm talking about one of the topics of chemical engineering under unit operations, transport phenomena. Okay, so there are three types of transport phenomena. Three. The first, we have the momentum transfer, or shall we say momentum transport. Second, we'll have the energy transport or energy transfer. Specifically, the example is heat transfer. And then we have also the last one, mass transfer. Okay, each transport phenomenon has its own formula and equation to govern so that we will be able to use that in different problem solvings related to transport phenomena. Okay, so I could not remember what number is this in unit operations because when I took up Bachelor of Science Chemical Engineering in Cebu Institute of Technology uh, University, I don't know the specific descriptive title. Okay, but it's only general unit operations, something like that. One, two, three, blah blah blah. And then when you go to that particular subject, and then it's in there that the topics by topics will be discussed. Okay, but there's no such telling this unit one is all about transport phenomena. This unit two is all about, for example, chemical and physical separation processes. And there's a lot also of physical and chemical separation processes. But for transport phenomena, there are only three. Okay. So in here, in this vlog, okay, we will be showing you the different formulas and equations to be used. Okay, like that. But before that, I'm going to refresh and to review the straightforward definition of each transport phenomenon. Okay, so we have the first one is the momentum transfer. But before we define, let we understand the term momentum. Okay, momentum it's discussed in physics. Okay, that's all about the mass of an object times the velocity. Okay, it's a combination between the scalar quantity and vector quantity. If you can remember the difference between a scalar quantity and a vector quantity. Okay, there's a lot of vector quantities. Okay, the difference mainly focused on the direction covered. For example, if we have the scalar quantity speed. Speed is equal to distance over time. Okay, something like, am I correct? Okay, and then velocity also is distance over time, right? It's still having the same unit, meter per second, like that, okay, or feet per second. Okay, but in velocity there is a direction from point A to point B, point C, point D, or it could be the north, south, east, west. For example, reporting the typhoon condition or tropical cyclone, something like that. Example only, 240 kph northeast, something like that. 112 kph southeast, something like that. There is a direction. This is a vector quantity. Okay, something like that. So this velocity is a vector quantity. Okay. So, for example, before giving the formula, we need to understand the scalar and vector quantity because this is very important also to distinguish if you incorporate these quantities into the formulas. Okay, like that. So, for example, for scalar quantity, we have the temperature, pressure, concentration, volume, intensity, mass, something like that. And the example of vector quantities are momentum, like that, okay, velocity, the force, the acceleration, something like that. And there is also another one, what we call as the tensors, okay? For example, velocity gradient, something like that, okay? We have the shear stress, the shear force, the tensile stress, something like that. The kinematic viscosity, the absolute viscosity, or something like that. The coefficient of diffusion of various materials, liquids, and gases, organic and inorganic liquids, or like that. And we have also the momentum flux, okay? Like that, we have also the mass diffusivity, or ganon. And then we have also the thermal conductivity, okay? And we have also the thermal diffusivity. So as you can notice, those are tensors quantities, okay? Usually transport quantities, okay, that we will be able to use in our formulas and equations in this three transport phenomena, okay? Transport phenomenon, which is the momentum transfer. So take note, mass of the object times the velocity as our basic formula from physics. Okay, something like that. So this momentum transfer is a transport or a transfer of momentum. Okay, like that in a fluid flow or fluid dynamics. Okay, something like that. If there is a fluid flow or a fluid dynamics, it's understood to be technically and scientifically there is a motion governed for the movement of those fluid and liquid particles. Okay, it's very clear. Motion. If there is motion, there is a complementary velocity upon the motion or the movement of this liquid and fluid particles. Okay, so the center and focus is for the study of fluid flow and the fluid dynamics. Okay, transport or transfer can be used interchangeably. Okay, it's just the same thing that as momentum transport, momentum transfer, because the word transfer and transport by English dictionary or any sources of dictionaries is just the same. Or it could be transmission. When you have that term, it's just basically the same as transport, transfer, and transmission. It's very clear that there is a movement and a motion between particles that could either be solid, liquid, and gas in a phases of matter. And this can be linked to a particles that could either be an atoms or a molecules or any substances, okay, of a matter, okay, something like that. So that's very clear. That's the first momentum transfer or momentum transport. Okay, and now I have a formula for that. Okay, so here's my pencil. Okay, guys, we should remember that carefully because this is the basic formula that we will be able to use in problem solving related to the flow of fluids, especially fluid that will goes and enter into the pipeline or conduit, something like that. Pipeline A, pipeline B, and pipeline C. So in this transport phenomena, we are not really focusing and concentrating to the mass and volume changes. Okay, that's why when we try to incorporate these quantities, the mass and the volume, we try to regard as a constant somewhere along the way, something like that. For example, if I have a very long pipeline, okay, so the gas, the solid, the liquid that will be able to enter the particular pipeline would have always the same mass, your process to produce the particular product. Okay? Because that's really routine to produce the particular product, then you have to feed constant amount forward in the chain in the production of cement. You feed it in that because it's usually constant and routine. Okay, feed that to the end of the pipeline. We are not really focusing and concentrating to the volume itself because the volume that will go there is just constant, somewhere along from point A to point B to point C. What we are interested for is that what type of flow for the particular fluid and liquid that will go into the pipeline could either be a laminar flow or a turbulent flow, something like that, or it could be a transition from laminar, then there will be a transition of flow, which is a turbulent flow, okay, something like that. So that's why when we incorporate the formula density is equals to mass over volume, we are not really focusing on the mass and the volume, but we are focusing to the transport property, which is the density, along with the viscosity, something like that, along with the momentum flux, something like that, heat flux, mass flux, okay, and diffusion coefficient, something like that. Now, going back to the momentum transfer, okay, I will show you the driving force. What's the driving force? Meaning to say, these are really the quantities that trigger to have a momentum transfer. Okay, without this driving force, then there will be no momentum transfer, or there will be no transfer from higher velocity molecules to lower velocity molecules because our transferring quantities are the velocity, okay, molecular velocity, sorry, velocity. Always say that molecular velocity, okay, molecules, something like that, okay? So from higher velocity molecules to lower velocity molecules, that's the concept of momentum transfer. Because in that, we have the mass of the fluid times the velocity of the fluid that will go into the pipeline, not only the pipeline, could it be a vessel, a tank, a process vessels, or whatever, tuba, as long as there is a flow of the fluid and there is a dynamic movement. That's why we call that as fluid dynamics. Okay, now I will show you the formula for that. Okay, so we need to consider the momentum transfer first. My gosh. Hello guys, you're still there? Sorry, the third part will be the problem solvings, okay? This is just only a presentation of formulas and equations, okay? Something like that. Okay, momentum transfer. Okay, in this topic, guys, when we speak about transport phenomena, then we have the term called flux. Okay, F-L-U-X. I will show you because this is very important. Okay, flux, F-L-U-X. Okay, like this. Okay, this is the rate of transfer over the area. Okay, like this. Over the area. This is the formula of the flux, the rate of transfer over area. Since we are starting with the momentum transfer, so it could be stated as flux equals to, okay, the rate of the momentum transfer over the surface area. This area is the surface area, okay? Good. It could be a pipeline diameter, then it could be pi d squared over 4, but then if it is just only dimensional rectangular or square, you will use the length times width, something like that. Or if it is a perfect square, we use s squared or s raised to the power 2 or psi raised to the power 2. But since pipelines like that or whatever process vessels are usually round, so that's why you apply the pi d squared over 4, the cross-sectional area of a pipeline, something like that. So you have to consider the diameter, the outside diameter and inside diameter, okay? And the radius also, and even the circumference, the 2 pi r. You also consider that one. It depends on the the question of the problem, okay? Something like that. Okay, this is the rate of transfer. Okay, now that's why if you listen to a certain sports announcers in TV like that, they will say, "Oh, this team A having a very high momentum," something like that, because the players are running, establishing a constant momentum because they are running. Okay, there's a velocity, something like that. There's also a mass of individual person. That's what we call it a momentum. Okay, so that's the term there. Always governed with velocity, okay, and the mass. Okay, but if there's no direction for that particular area, then it would be a speed also can do. Okay, but in here, direction is very important. Vector quantity. Okay, momentum transfer. So momentum transfer. So our flux will be momentum flux. Okay. This momentum flux is also called as a shear stress. Capital S, small letter HEAR, and then stress. So this is really helpful for the learning from the I think strength of materials and engineering mechanics, because it deals with tension, right? If you can remember, tension, stress, like that, okay, in the bridge, and you have to compute for the total force going downward, going upward. Engineering mechanics are more on strength of the materials. Okay, one of the major subjects of civil engineering course. Okay, so that principle will be applied here because momentum flux is also a shear stress. Okay, like that. Okay, shear stress is basically the same, having the same analogy with the pressure. Okay, something like the formula here will be force over area. Okay. The only difference, class, for the momentum flux and shear stress, actually this is also force over area. Okay, but the force here is the shear force. Okay. If we have the shear stress, then we have the shear force as our numerator. Again, the area will be our denominator. Okay. Shear force. Okay, now since we have the rate of transfer, okay, the rate of transfer can be best described by inserting the delta change, something like that. Delta change for this quantity per delta change of this quantity, something like that. But in case of transport phenomena, okay, our numerator will be basing only for the momentum, to the mass, and to the heat, because those are the transports that we are referring to. First, momentum transfer, right? Like that. So, mass times velocity, right? So we have, I have to put like this. Okay, but before that, we need to consider also the viscosity. Okay, viscosity is very important in the momentum. Why? Explain to me, class, why viscosity is very important. Okay, if we have the resistance in Ohm's law in electricity, practical electricity knowledge, which is voltage is equals to I times R, like that. And I is the current or electricity, the movement or the motion of electrons from one point to another, or from one path to another. And then we have also the resistance that opposes the, the voltage, something like that. Okay, that's why it's called resistance, to resist, from its word alone, right? This viscosity have the same principle with resistance. Okay, and this quantity is or transport quantity, of course, the transport phenomena. Okay, because transport phenomena is more on the fluids. Okay, like that. So viscosity is a measure of fluid's resistance to flow. Okay, there's always a resistance. If there's no resistance, then a lot of wastage will be going to the land, something like that. Okay, it cannot be controlled. Aside from the orifices in the pipeline, right? Aside from the valve, or what shall we say, the elbows that can control, regulate the volumetric flow rate of that particular liquid or gas that will pass in the pipeline, like that. So we need also to have resistance for the flow, or else so many will go or wastage of our fluids into the ground or whatever. Okay, so we have a measure of the fluid's resistance to flow, and that is viscosity. And then you have to multiply that for the rate of momentum transfer. Okay, I have two more for this. I have viscosity. Let's denote that as like this. Viscosity, and then specifically kinematic viscosity. Wow, bongga. Okay, this is the kinematic viscosity. Okay, this is a symbol to differentiate from the speed, which is v, and also for the volume. Okay, so we need to to change the appearance so that we can distinguish what is a viscosity, a volume, and a velocity, right? Because usually we represent that as a v in physics. Okay, the velocity, something like that, and the viscosity also sometimes v in other explanations of some textbooks also. Okay, in fluid dynamics. Okay, like that. So let's agree that our kinematic viscosity would have a symbol like this. Okay, this kinematic viscosity, guys, is also the same as momentum diffusivity. Ganon. Okay, so it's the same terms only. So inject that in your brain cells, because sometimes in examination it will be asked. For example, mass diffusivity is just the same with a coefficient of diffusion, like that. A false, B true, none of the above, something like that. Okay, you have to memorize that this kinematic viscosity is the momentum diffusivity. Okay, since we are now done with the definition of the viscosity, then we have to have definition also. What is a diffusion? Okay, normally molecules that will undergo a fast diffusion are gaseous molecules. Okay, gas. And then second will be the fluid or the liquid, okay, basing on the diffusion rate. So by the way, what is really a diffusion? Okay, that is a momentum spread between the particles. Again, momentum is there, meaning to say the velocity and the mass of these gases, liquids are being spread, okay, between, okay, particles. It could be an atoms or molecules of a matter. Okay, again, matter is anything that occupies space and has mass, and technically those are solid, liquid, and gas. Okay, so this solid, liquid, and gas composed of molecules, and these molecules composed of atoms. And these are all what we call as particles. Okay, because the definition states like that it is a momentum spread between particles that can either be in atoms or molecules of matter. Okay, and of course, this can also be attributed by the external pressure. Okay, external pressure and the shear stress. Okay, this is momentum, right? Okay, like that. Going back to the formula, we insert the kinematic viscosity or the momentum diffusivity times the rate of momentum transfer that could be stated as delta change. Ganon. Mass times velocity, which is the momentum, of course. Okay, mass times the velocity. Let's put velocity as u, small letter u. Okay, to distinguish from the volume, which is small letter v, right? Okay, over the dx. So Sotero, what is dx? X is a horizontal position. As we can remember in our algebra, there is always y-axis and x-axis. Okay, but in transport phenomena, our dx should always be in a horizontal position, but our y-axis, that is, we will vary in the each transfer. That could either be a momentum transfer, okay, a heat transfer, and a mass transfer. So dx always meaning horizontal position. That's why in a momentum transfer, the change is always from higher velocity molecules to lower velocity molecules with respect to the horizontal position of the fluid. Okay, with respect or relative to the horizontal position of the fluid or a liquid. If we speak about from higher velocity molecules to lower velocity molecules, there's a change involved in that final minus initial. So this is what we speak the term gradient. That means a difference from the final and the initial state of that particular quantity could either be a vector quantity or a scalar quantity. But in this case, momentum is a vector quantity. Okay, something like that. And we need to say momentum 2 minus momentum 1, final minus initial. Okay, like that. But it's written as mv, the rate of momentum transfer. Now, as I told you earlier, we are not really concerned with the mass, right? Now, we need to eliminate that in the theory because we are not really focusing with that. Then why you should involve that one? So common sense. So we should remember the formula in chemistry. Okay, density is equals to mass over volume. Okay. Density, we represent density as rho. Rho meaning Greek symbol. Okay, Greek meaning Greece. Land called Greece, and the people are called Greek, right? Am I correct? And then it will be called as Greek symbol, alpha, theta, okay, theta, phi, sigma, something like that. So, right? So those are symbols, or I think Greek symbols, okay? Like that's density as a rho, RHO, something like that. Am I correct? Okay, go back to the density like this. We change the density because maybe there is the same also symbol somewhere along the way. Okay, this is the rho. or the density is equal to mass over volume. Okay, like that. Now, in our momentum rate of transfer, okay, rate of momentum transfer, okay, there is a mass. Then compute for the mass in here. So mass is equal to density times the volume. Substitute that here in this equation. Okay, so kinematic viscosity times the delta change of density times the volume, okay, times the u, which is the velocity, okay, like this. Okay, I'll just substitute that one. So mass cross multiply, we can obtain algebra, okay? Density times volume, then substitute the formula of mass in this equation. It will become now the density times volume times the u, the velocity, over dx, the horizontal position of the fluid. Okay, ganon. So like this. So this is our standard formula of momentum flux or shear stress. Okay, momentum flux, let's have that as a small r, okay, like this, or a shear stress, something like that. And this one is our formula, okay, like that. So r, which is our momentum flux, okay, is equal to r is equal to this one, the kinematic viscosity or the momentum diffusivity times the volume times the velocity over dx, which is the horizontal position of a fluid. Okay, something like that. It's very clear, huh? Okay. If the question will state like that, what is another term of momentum flux? And your choices will be A, ganon, B, C, D, and your answer will be shear stress. Okay, because shear stress and momentum flux is just equal in fluid dynamics and in fluid flow or in transport phenomena. Okay, and now we go to, and now the time is near. I did it my way. I did it my way. Ganon. Okay, this is number one. And then we go to number two. Oh my gosh. Heat transfer. This is very interesting. I love heat transfer. Yes. That's why I told you a while ago, I love transport phenomena. This is one of my favorite, subjects in chemical engineering, really. Okay. And then I focus on this. And it's just a timing that during the chemical engineering board examination, there's a lot of momentum transport phenomena, like us. Transport phenomena topics then. I was just lucky, okay? And there's only few distillation, like that. I don't like distillation, okay? And there's a little bit of flotation, screening, filtration, ganon, drying, something like that, leaching, okay, something, but more on really transport phenomena. I love it, okay? I love concentrations, it transfer. Okay, that's why it always starts with a chemical reaction, right? Okay, it depends on the forte of the individual also. Because if you don't like really the topics, then you are very tired of studying that one. You are really forced to study because you have to attain a good grades. For example, if you're academic scholar, whatever like that. Okay, so you have to maintain grades. That's why, and you have to pass really. Okay. Number two, heat transfer. Oh my gosh, heat. I love heat. So what in thermodynamics, I think in the first law of thermodynamics, okay, I don't think so. I think lang ha, based on my stock knowledge, thermodynamics, Q is equals to mc dt, and this is also discussed in physical chemistry. But actually, the basic foundation is really discussed in general chemistry. Okay, somewhere along in the middle of the topics in general chemistry. Okay, Q is equals to mc dt. Okay, wherein Q is the heat, it could be the sign. Okay, it's in this concept that not all heat are hot. It should also possible cold, and that is negative heat. Okay, so because other people are saying if it is hot or heat, it's no longer not practical to have a heat that is negative. We have that one also, okay, in studying thermodynamics. Okay, that's why refrigeration system occurs. Okay, refrigeration study. Okay, like that. And in the HVAC through refrigeration system, you can write the compression, like the expansion, study and knowledge. That's part of thermodynamics. Okay, that's referring to heat. Okay, something like heat absorbed, heat released. Okay, like that. Okay, when heat is being absorbed, it is being consumed, then you have a endothermic reaction. When the heat is being released and given off and exposed to a certain environment, that is exothermic reaction. And most of the chemical reactions will undergo exothermic reactions. Though there are also some that are endothermic reactions, but most of the chemical reactions really are exothermic reactions. Okay, a lot are irreversible reactions. Only few are reversible, meaning it will goes back to its original reactants after the products being released. Okay, like that sound. Okay, heat transfer. Oh my gosh, I will write the Q is equal to MCP dt. Okay, Q. This is really basic. Q is equals to MCP. Again, dt is a delta change, meaning final and initial temperature. Okay, so in here you have to memorize. Okay, so the different temperatures units, the degrees Fahrenheit, the degree Celsius, okay, the Kelvin. Don't confuse, Kelvin has no degree, huh? Only Kelvin. Okay, it's not degree Kelvin, it's only Kelvin because there's no small letter zero at the top. We don't ever say degrees Kelvin, it's always Kelvin, which is degrees Celsius plus 273.15. Okay, and then we have also the Fahrenheit, okay, which is 9/5, something like that, right? Times degree Celsius plus 32. Am I correct? Okay. And then we have the Fahrenheit is 9/5. Okay, like that. Okay, because that's B compared to the Celsius. And the Celsius is 5/9, then degrees Fahrenheit minus 32. Okay. Again, degrees Celsius is lower. That means 5/9 times degrees Fahrenheit minus 32. And then if it is degrees Fahrenheit, it is 32. Okay, degrees Celsius. Okay, you have to convert that one because in dealing with ideal gas law and non-ideal gas law, okay, you have to use that one also because we have the universal gas constant or the general gas equation constant. Okay, remember that one, the capital R in the PV and RT formula also. But we don't have to touch that here. Okay, maybe we can apply that also in the mixture of this momentum transfer. Because there's also a problem that we need to combine the ideal gas law and in the momentum transfer. Because the momentum transfer is not limited to fluid. You should also apply the gas in certain situation. Okay, but it's not common. It's more common in the fluid. But you know, problem solving, you cannot expect attention ability of the student or the critical thinking of the student during examination. Okay, like that. So we have Q is equals to MCP dt, M is the mass of an object. I'm telling you object, meaning it could be a liquid, it could be a solid, it could be a gas. Okay, and then Cp, it should be the specific heat capacity. Okay, for the water, as far as I could remember, that is 1 calorie per gram degree Celsius. Correct me if I'm wrong, that's only registered in my brain cells, but I think so it's called, okay, specific heat capacity or the heat capacity. And then we have to multiply that with the delta change in temperature, like that, and transfer. Okay, in heat transfer, we have 3 modes of heat transmission. We have the heat transfer of convection, the heat transfer of conduction, and the heat transfer through radiation. And each heat transfer or heat transmission, you should understand, okay? And you should memorize the basic concepts out of it, especially the theory, okay, for that. And then after having the thorough and adequate, okay, I advise you guys not focus directly to the formula and equations. Focus first on the core foundation, which is the theory, okay, theory, principles, and concepts, because you will be lost somewhere along the way if the problem is these quantities, and you will be lost because you are used to for this only, and you don't have an idea that it's just the same, like that. Just like this, a momentum transfer. Shear stress can act also as a pressure. Then if you have no knowledge, then you cannot compute for the force or the area. If the question will say, what is the pressure of the following, the shear stress is given, but it's not given in pressure. But we know that pressure can exist as a shear stress. Okay, so you cannot get the answer. Okay, if you don't have the thorough theory and concept. Because this shear stress have the formula of force over area, the same as pressure is equal to force over area in chemistry or in physics also. Okay, so it's very clear. So it's have the same unit. Okay, of course. If you substitute those quantities, you can attain the same units. Okay, because force over area, something like that. Okay, going back to the heat transfer. Okay, heat transfer is the transport of the molecular temperature. Okay, molecules in terms of temperature. Okay, you know that one? So temperature is our basis from higher temperature to lower temperature. So the question of molecules from high temperature to lower temperature, the same as with the momentum transfer, high velocity molecules to low velocity molecules. Here also, high temperature to lower temperature. Okay, now here is a trick. Some book putting only energy transport. Okay, so basically, if you try to be more, imaginative, or let's say, we have we take into a bigger perspective or a big picture for the topic. So we need to say pala, transport phenomena is composed of, okay, the momentum transfer, the energy transfer, and the mass transfer. And this energy transfer, heat transfer is only the example. Okay, but there's a lot to that. We have chemical energy, mechanical energy, electrical energy, pneumatic energy, hydraulic energy, thermal energy, gravitational energy. Radiation can be considered also as an energy. Okay, light energy coming from the sun. So those are energies, and kinetic energy also, and potential energy. So actually, these are also under energy transfer, energy transport. But since we are dealing with transport phenomena, we are focusing only to the one example, which is the heat energy. That's why we have heat transfer. But actually, there's so many energies. That's the chemical engineering focusing on. Okay, from first year to fifth year college. Those types, all types of energies I mentioned a while ago are being covered by the BS Chemical Engineering course. Okay, the electrical energy. Okay, mechanical energy, chemical energy, light energy, gravitational energy, thermal energy, radiation energy. Okay, pneumatic energy, hydraulic energy. Okay, hydrothermal energy, geothermal energy is another thing also. And we have the light energy coming from the sun. So there are at least 13 energies, including the radiation energy, 14 energies, okay, that made us survive in this contemporary world. Without those energies, all of us will die. Okay, especially the heat energy. If you don't have heat energy, then we cannot burn our, fatty acids to be released outside from our body. The toxins, the harmful substances, okay, it cannot be released. So there must always be heat energy, and the process is through metabolism, okay, breaking down of calories and fatty acids, something like that, or the breakdown of glucoses from our body, coming from the carbohydrates, something like macromolecules in biochemistry. Okay, going back to the again, heat transfer. Again, heat transfer is the transport of energy, okay, molecules, specifically the heat energy, okay, from higher temperature to lower temperature. So it's always heat. When we deal with temperature, it's always heat. Now, we go to the formula. So, if we have the momentum flux, we have also the heat flux. Unsa ganitong flux? Flux is the rate of transfer over area. And the rate of transfer could either be a momentum transfer, a heat transfer, and a mass transfer. Okay, like that. That's why we call this a heat transfer flux. Okay, heat transfer flux. Okay. Heat transfer flux is denoted as capital Q. Okay. Like this. Capital Q. Okay. So flux is equals to the heat numerator, small letter q, over area. It's not a flux, but the heat specifically. Okay. Now, we have the formula, this Q is equals to mc/dV, substitute. Okay. But I will change the capital Q to small letter q to agree with this, huh? I will change for the purpose of agreeing only. Okay. So Q is equals to mc/dV. Substitute the mc/dV here in the numerator. Okay. So mCp dt over, since this is for the horizontal position, that is dx. And then delta change of this small letter q. So this is now our rate of heat transfer. Delta change of mCp dt over delta change of x. Actually, this is y. And we are only having a specific quantities that will be inserted in the y. This is actually dy dx. If you can remember the differential calculus, okay, dy dx always, and you have to differentiate that one. Okay, it's just we're always constant because horizontal position is always in the denominator, numerator, okay, like that. So this is our, like this. And before that, we should always multiply with the, okay, heat transfer diffusivity. If we have the mass, if we have the momentum diffusivity for the momentum transfer kinematic viscosity, here we have the heat transfer diffusivity. Charot. So, i-denote lang nato siya alpha. Forget first the alpha particle, alpha emission, alpha ray, but we are focusing here on transport phenomena, okay? Like that. So alpha will be our heat transfer, which is this quantity, okay? Like that. Okay, now, again, we have the mCp dt. What is the formula of M in terms of volume? Again, density, the same as the momentum transfer. Density is equals to mass over volume. Okay, find the value of M, which is the mass of the fluid. So M is equals to density times volume. Substitute the density equals to mass over volume. Then we need to find the mass, substitute that here in the mass. Okay, and then our answer will be this one, density times volume, substitute that here. Okay, okay, alpha delta change in density rho. Okay, I almost forgot, right? VCP dt over dx. Okay, this one. If you substitute this, it will become like this. Now, again, in the theory, we are not focusing and concentrating to the volume, because the volume throughout the process is just constant somewhere along the way. For example, again, I repeat this always, I have a 20 feet pipeline. Okay, of course, the volume will go there. It's always 20 20 liters also. Okay, you remain constant, the same as the shape of the pipeline. It will occupy, okay, or else it will overflow if the volume is not enough to fit the pipeline, right? So it's just constant all throughout. Then we have to cancel this V because we are not interested with this V. We treat that as constant. As you can notice, every formulas discovered after the scientific laws of our scientists, they always have constants. Okay, the purpose of that for to simplify the formulas, not to complicate so many quantities to be inserted, and also to agree and to cancel out the units. Okay, like that. Because volume, we're not really interested with the volume for transport phenomena. Okay, if we don't know, so it depends on the problem also, but most of the times we are not interested in this. We will cancel that one. So our heat transfer flux will be alpha times d raw density Cp specific heat capacity or heat capacity. Sometimes the specific heat capacity can be termed only as a heat capacity. Don't be confused also. Okay, times dt. Okay, like that. And this will be your formula for heat flux. Okay, this one. Okay, heat flux capital Q is equal to heat flux or heat transfer flux. It's just the same, huh? You could say heat flux or heat transfer flux. Don't be confused. It's just the same thing. Q is equals to heat transfer diffusivity. You should remember the one you will multiply with this, okay, delta change of the heat rate of heat transfer is always the diffusivity. Okay, diffusivity times D raw density times Cp times delta change temperature, temperature final temperature initial, and dx horizontal position. Okay, something like that. Okay, now we have the heat transfer equation already for this. Okay, so like that. Some books also are not stating that one, but ako rin siyang gitoki. Okay, that's why I come up with this. Because the books are not really, spoon feed. Where did you get this, like this? And don't even saying that this will become a constant, that's why it will become a cancel. It will be cancelled. There's no such explanation to that book. You will be the one to analyze, okay, ganon. So sometimes you have to, analyze, we treat that as constants pala siya. Ganon. Okay? And then we go to the mass transfer. Oh my gosh. Mass transfer, I love this also because it's talking about concentration. Oh my gosh. Concentration of the chemical substances, raw materials, products like that. Okay? Especially equilibrium concentrations. I love the topics, really. Okay? So this is mass transfer. So we can have the mass flux also, okay? So we can denote here is very special, Charon. Okay, we denote a special letters, GA, as in June, okay? GA, capital A, okay? Mass transfer. Oh my gosh. Okay, denote that as a GA, okay? Okay, GA. This is mass transfer flux or the mass flux. Okay. Don't be afraid, huh? It's just the same. Mass flux or mass transfer flux, something like that. Okay. So GA is equals to NA over A. Always the area is the denominator. Okay. Okay. Our NA here is the rate of mass transfer. Okay, rate of mass transfer. So this is gonna be, again, the same thing. Okay, diffusivity here, we have the mass diffusivity. So we can denote that as capital D, A, B. Special talaga ang mass transfer. Okay, so D, A, B. Okay, times Okay, and this Na, of course, we're referring to the concentration. Okay, bear that in mind. Mass transfer dealing with concentration. Okay, like molecules concentration. Okay, like that. So DAB. So T. So concentration meaning Ca. C stands for concentration. Okay, Ca. Like this. Over Tx. Like this. Ganon siya. Okay? The mass transfer flux or the mass flux denoted as Ga is equals to Na over A. This Na is the rate of mass transfer. Our mass transfer is this one. Okay, and this diffusivity. This one is the mass diffusivity, okay, and times with this dCA over dx, horizontal position, x, and this is the y supposedly. Okay, since we have a specific quantity, then we will substitute this concentration. It could be final initial, or it could be here alone if there's no final or there's no initial, something like that. Only given one concentration. There are problems like that also. There's only one concentration given, like blah, blah, blah. And then that would be automatic your concentration here if there's no two reference points. But if there's a reference, initial, final, then you have to subtract. So that's a gradient, concentration gradient. Remember this in science, gradient meaning a difference from the final state and the initial state. Could either be any kind of quantities. It could be temperature, it could be volume, it could be voltage or mass, it's blah, 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 so on so. Okay, that is gradient or difference. Okay, so velocity gradient. Okay, velocity final minus velocity initial. Okay, speed gradient, speed final minus speed initial. Concentration gradient. Okay, concentration final minus concentration initial. Ganun lang siya. Okay, so that's it. This is the mass transfer. Now, so Sotero, what do you mean by mass diffusivity? Okay. It's very far from the symbol D, okay? Because this is a diffusion coefficient. Another term, right? So don't forget this. Put this in your brain cells also, that mass diffusivity is also a diffusion coefficient. Okay? What is really a diffusion coefficient or a mass diffusivity? This is really give an information for the association of the smaller molecules, okay, to the macromolecules, especially in the topics of, biology, okay, or in the tissues, in the cells. Because, molecular substances could either be macro or micro, okay, or biochemical substances. That's what we call them, because it's a combination of chemicals and biological substances. That's why biochemical substances. A biochemical substance is composed of micro and macro, meaning micro substances and macro substances, or micromolecules and macromolecules. Okay, the food we eat are macromolecules. Okay, like for example, carbohydrates, nucleic acids, protein, amino acids, like that. Those are carbohydrates, sugars, cholesterol, something like that. Those are macromolecules, but there's still micromolecules also. Those are, I think, the enzymes, blah, blah, blah. Okay, so smaller, the probiotics, the good bacteria in our body, something like that. Okay, so composed of that, that's biochemistry, but we will never touch that there. Those substances, have diffusion coefficient. They will move, they will diffuse there inside our body during the physiological reaction in the anatomy of our organs to organs. Okay, there's a reaction there. They will diffuse. We have also a diffusion coefficient, meaning we have to associate the smaller molecules into the macromolecules. So because it's impossible that it will just come up directly as a macromolecules, it will start also from a micromolecules, and then it undergo a synthesis reaction or a polymerization reaction or a combination reaction to produce macromolecules. It will start with a very tiny molecules and a micromolecules before it will become a macromolecules, right? That's why this diffusion coefficient will be applied to produce a large molecules or a macromolecules. Okay, fats are macromolecules also. Okay, like that. That's why that's the definition of diffusion coefficient. That's also the same with mass diffusivity. Okay, in the mass transfer flux point of view. Okay, so these are all the formula that we'll be able to use in the transport phenomena: momentum transfer, heat transfer, and mass transfer. Now I have also to introduce you another formula, which is the Reynolds number formula, which is the basis for fluid dynamics and fluid flow. You could either determine it as a laminar flow or a turbulent flow. Okay, if it is a laminar flow that is less than 2000, okay, and then if it is a turbulent flow above 4000, and somewhere in between is the transition flow, something like that. Okay, so that's Reynolds number, Re. I will show you the formula now because it's very important in fluid flow, fluid dynamics, which is the momentum transfer. Okay, Reynolds number really is a unit less. Okay, so Sotero, why do we have to get this Reynolds number? Okay, because this is the ratio. Okay, this is really the ratio of internal viscosity, okay, to the kinematic viscosity, something like that. Okay, or it is a relation with the internal velocity or absolute velocity ratio with the kinematic viscosity or dynamic viscosity, something like that. Okay, internal viscosity and then the kinematic viscosity ratio niya siya, ratio. Okay, that's why we need to get this Reynolds. This is the basis. Okay, because the viscosity is the resistance of fluid to flow man siya. Okay, so that's why. So Re is equals to the length times the density times the velocity u over the viscosity, which is the kinematic viscosity, ha? Okay. But some books also I read, the kinematic viscosity will behave also as an absolute viscosity. Okay, in a turbulent, no, in a laminar flow, something like that. Okay. But just use viscosity alone without label. It's just same thing for now. Okay, unless specified there that is really a kinematic because it's the same. Okay, so Reynolds number is equals to this one. Okay, Reynolds number is equal to the length in meters. Okay, we are using S. No, not SI. We are using the SI. We are using the SI. Sorry. No, it's not SI, metric. Sorry, metric, because meters, kilograms, seconds are metric, right? Based on my memory, okay, like that. Okay, so Reynolds is equals to the length, okay, times the density, times the velocity u. Okay, velocity will be meter per second. Okay, density will be a kilogram per cubic meter. Okay, and then this length is meter, so all will be agreed. That's metric system. Okay, and then the kinematic viscosity is also a metric system, which is the Pascal second. Okay, Pascal second. Okay, or it could be a kilogram times meter second. Okay, like that. Kilogram times meter second, like that. Okay, or it could be a Newton times seconds over square meter. Very difficult, right? Transport values are very difficult, really. That's why we need to rely the chemical engineers, the theories chemical engineers handbook to get the transport properties values. Okay, what are those? The density, the kinematic viscosity, the absolute viscosity. Okay, the thermal diffusivity, the thermal conductivity. Okay, the diffusion coefficient. So these are transport properties. and this cannot be sometimes be inputted in the problems. Okay, you will try to find out this in table blah blah blah. As far as I could remember, there's a table 2-21 for density of a water at certain temperature. For example, water at 30 degrees Celsius, meaning to say water is a pure substances, right? So that is a table for pure substances. Table also for inorganic and organic liquids. A lot will be there, and it's a parameter, 30 degrees Celsius, what's the pressure, what's the equivalent, blah, 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 concentration. Then you can substitute for the formula there somewhere in the particular table. There's also a special formula there, okay? And then before you substitute that here, you should substitute that first in the original formula in the chemical engineer's handbook, okay? Like that, or in the chemistry books also, because chemistry books also have physical chemical data. That is called physical and chemical data, or physical and chemical properties data, okay? Like that, a lot, okay? So you have to check it out there. And then if the problem already given that completely, then bingo, you can directly substitute. Okay? But most of the times it's not really direct substitution. Okay? It requires you to get on the handbook. It will take time also, especially when you don't know where this table like this, and you will panic. Really, you will panic really, especially in the actual examination. Oh, where can I get this table like this? Especially the psychrometric graph. As far as I could remember, it comes out in the board examination. Oh my gosh, where can I find this one? Okay, and then you have to determine like this, the heat. That was thermodynamics really. I was panic. Okay, like that, and then I don't know where is that in the handbook. Okay, like that. So be ready and be prepared to quickly identify the table, the specific table for the particular topics. Okay, especially physical and chemical properties. Okay, like data. Okay, this one. This is the Reynolds number. Okay, like that. So if the question was this, blank is a number that will determine the internal viscosity against the kinematic viscosity, like that, blah, 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 so and so. Then it will answer with Reynolds number. Okay, like that. Okay, and the other one will be involving the mass flow rate and the volumetric flow rate. Okay, so mass flow rate meaning M, volumetric flow rate means F. Okay, so let's have this. Makalagot because the book are showing Q also in the mass flow rate. I hate it. Okay, because it really makes the other also. We lit this Q only in the heat, right? But he also put the Q in this, formula. So, it makes us confused also. Q is for the, here, the book I referred something like that. Q is also the, the mass flow rate. And Q also is the heat transfer rate somewhere along the way here. So, of course, the student will confuse. We need to, to isolate or to differentiate or to give a difference, then give another symbol. Okay? So that we will not be confused. Let's just have a symbol M, small letter M, right? Or capital M lang siya. Oh, molar man sa capital M. Uy, sabi ng Jude, wow, mass flow rate will be, lang siya. Ganun lang siya. Parang McDonald. Okay? M. Mass flow rate just like a symbol of McDonald because the capital M is symbol of a molarity. Molar. The small m also is a symbol for the mass. So to make it different, M like a McDo symbol is our mass flow rate. Wow. May ganun. Okay. Mass flow rate is equals to the velocity U times pi d squared over 4. Okay? This one. Mass flow rate is equals to pi d squared over 4. Pi d squared over 4 is really the area, the cross-sectional area of the diameter, the circle, on the inlet of the pipeline. Because it's always round. Tank also is always round, right? So this is always be like this. We are not dealing here with a dimensional rectangle because process vessels is not really rectangle. or square. Though others have, but most of the of the lines to lines are always pipeline like that, round always. So we need to use this most of the times. Sometimes there's a cone also, but most of the times always this. Okay, especially pipeline. Okay, pi d squared over 4. And then if we try to consider the volumetric flow rate, if we have the mass flow rate, of course we can get the volumetric flow rate through the formula of density again, mass over volume. We just add flow rate in it. Okay, density is equals to mass over volume. Okay, so we can also say that density is equals to mass flow rate over the volumetric flow rate. Okay, the same here. Because there's no such density flow rate. It's not, there's no word like that. Always mass flow rate and volumetric flow rate. But what I am telling you is just the same formula we'll be able to use. So density is equal to mass over volume. Then mass again, density times volume. Then this density times volume, substitute this to the mass here. Okay? And then we can simplify that at density times volume is equals to velocity pi d squared over 4. Pi d squared over 4, ganun. And then compute for the value of the volumetric flow rate, V. Capital V lang volumetric flow rate because we have the small letter V man siya sa, sa volume. Right? Volume, small letter V. So, ibig sabihin, pag capital V, volumetric flow rate, small letter V is the volume alone. And then for the U is our velocity. Kinematic viscosity itong may ganon. Parang ganon. So that we can identify, okay? So, volumetric flow rate is equals to divide this by D to solve for the value of V. Okay? Like that. So, volume is equals to ganon. Pi d squared over 4 over density. Okay, and then we try to reverse that one. So velocity is equals to U times pi d squared over 4 over the density. Okay, so like this, 1 over density. So this one. So this will be our formula. Volumetric flow rate is equals to velocity pi d squared over 4 over the density, rho. Ito. Hindi na maklaro, no? This one. Okay? Maklaro pa ba siya? Okay. So, dyan maklaro. Gamay na dyan siya. Basta, density is equals to mass over volume, compute for the mass, and substitute also for the, here, mass flow rate. This is also M. So substitute the value of density times volume here and solve for the value of the capital V, which is the volumetric flow rate. So you have the formula of volumetric flow rate. Okay, velocity times pi d squared over 4 over the density is equals to V, volumetric flow rate. The unit will just cancels out if you put specific units and do not mix units. It should be simplified all the time. So these three equations I'm showing you is very important to determine whether the flow of fluid is laminar, the transition stage, and turbulent, something like that. So that's all. So these are all the formulas. So before I end this vlog, I will tell you that the theory behind. Okay, the one who discovered this momentum transfer is also Isaac Newton. Okay, apart from his three laws of motion in physics, which is the law of inertia, the law of acceleration, and law of interaction, right? 3 laws. He also promulgated this one. That's why this is called Newton's law of viscosity, this momentum transfer. And then the second, which is the heat transfer, is discovered by Fourier. So this is now Fourier's law of conduction. You don't mix this one, huh? Okay, and then the other one is the mass transfer. This is discovered by Fick's, Fick, Fick's law, or what we call as Fick's first law of diffusion. Okay, so if the examination in the future will say what is being used, what law is being used in the mass transfer? A. Albert Einstein theory of relativity. B. Le Chatelier's principle. C. Arrhenius theory. D. John Dalton. Okay, and letter E. Fick's first law of diffusion. Your answer will be Fick's first law of diffusion, the basis of mass transfer. Okay, like that. Because there's a lot of theory, right? If you sum that all in one notebook, there's a lot. Okay, there's a Henry Becquerel theory of radiation, radioactivity, sorry, and the X-rays by Roentgen, something like that, blah, blah, blah. Okay, and a lot. G.G. Thomson discovered, ganon, ganon. Okay, electrons, whatever. Okay, okay, that would be enough. Okay, just remember that one. Thank you so much for watching this vlog or a live stream specifically. If you think you get a little bit of information, then share to anybody else. If you aren't yet subscribing, subscribe this channel and then click for the notification bell from some newest updates of I Am Seeing Channel Voice. Okay, see you later. Bye bye. See you later for the part 3 for problem solving. Thank you so much. Bye bye, everybody. Okay.